All right, welcome. Let's begin. You've got a homework assignment due on Tuesday, and part of that includes the fluid acceleration stuff that we're talking about today. Part of it is having to do with flow visualization and streamlines, streak lines, path lines that we did the activity in the previous class, and so you can get an early start on that. If you've got any questions, stop by my office. So let's get right into it. We're going to be talking about the movement of fluids, and a big part of why we do that is just because in civil engineering applications, most of the time the fluids are moving. So we're going to consider two different types of acceleration. And this diagram is showing that we can look at the velocity of a fluid particle as it moves in the s direction. So here S is just referring to its position. And you can see that it has a velocity at a particular time, but velocity is a function of both s and t, meaning that it's possible for a particle to be accelerating on two different bases, the basis of its position and the basis of its time. And so we'll look at different illustrations of that. First of all, acceleration with respect to time, which is the type of acceleration that most people think of. When you hear the word acceleration, you think back to your high school physics class where you were talking about the change of velocity over time. And that's the more commonly understood definition of acceleration. Wait for a little video here. And this is a particle that accelerates much more quickly than any of the liquids that we'll generally observe. Computer isn't very quick, though. Still loading. All right, it's a rocket sled, and you can see that at the beginning, it's at the end of the track, it's not moving, but when the rocket's fired, its velocity is increasing very quickly. Yeah, I think that they were testing an ejection seat there. So let's watch it one more time. From the beginning. From the very beginning. All right, there the rocket burns. Accelerates. I don't think that's a person. I think it's just sort of a dummy in there. All right. So that is an example of the change in velocity with respect to time. And here's another example of how the speed can be constant, but yet there's still acceleration. Now, I don't know if any one of you have been in something like this, but you've probably seen it in movies before, that astronauts get trained in little devices like this where it spins around in a circle, and even though the rotational speed may be constant, the person inside is still experiencing an acceleration. So how is that possible for there to be an acceleration when the speed is constant? The velocity is changing, but the speed is the same, so how can the velocity be changing? It's the direction, that's right. And so this is a tangential acceleration. Seems like that'd be a pretty uncomfortable ride. All right, so there's acceleration with respect to position, and there's acceleration with respect to time. And remember, last time in class we were talking about steady flow and uniform flow, and how steady flow is when the conditions are constant over time. Unsteady flow, we watched the video of the flash flood in Arizona, where from one time to next the flow conditions were different. Uniform flow is where the velocity is constant with respect to position, meaning that the streamlines are parallel. And so these two different kinds of acceleration use different equations for us to try and identify how pressure is changing with respect to the acceleration that occurs. And that's often the question that we're trying to ask is, what is the pressure in a fluid at a certain location? When conditions were static, we had it pretty easy because all we had to do was apply the hydrostatic equation, which is just simply as you go deeper down into the fluid, the pressure is increasing according to the rate of gamma. But when the fluid is accelerating, the pressure changes even horizontally. And so we have to be very careful in the way that we consider the effective pressure of acceleration on pressure. All right, so let's consider local acceleration. Local acceleration is the change in velocity, here assigned the variable u, the change in velocity with respect to time. And that can be the direction or the magnitude of the velocity is changing with respect to time. So it can be a rocket vehicle, it could be a rocket sled. As long as it has to do with rockets, then there can be a local acceleration. Even actually you don't need rockets for there to be a local acceleration. It's just maybe more interesting when it is. Now here is something that's a little bit less familiar to people in terms of acceleration. This can be acceleration as a function of position. And so convective acceleration. Now consider the diagram that's shown here of a nozzle that's contracting in its diameter. When flow comes into the big part of the nozzle, the velocity of the flow is 10 meters per second. And then as the nozzle contracts, what it's doing is it's forcing the same amount of flow into a smaller cross-section. And so because of that smaller cross-section, the fluid has to speed up so that the same volume can squeeze through a smaller area in the same time increment. And so the speed goes up. So you can see as it exits that nozzle, the velocity is 20 meters per second. And so there's a change in velocity, but it has nothing to do with time. In fact, we could have steady conditions, meaning that now it's 10 at the entry, 20 at the exit, or an hour from now it's the same velocities of flow. We can have steady, but still see an acceleration. And so here the acceleration has to do with position within the flow field. And if you look at the shape of this nozzle, it seems like at the entrance and near it, the nozzle walls are more or less parallel to each other, which means that the fluid isn't accelerating right at the beginning. But then as the shape of the nozzle is changing, then that's sort of where the acceleration is occurring, is when the when the diameter is decreasing, that's when the flow is speeding up. And then here again at the exit, the walls of the nozzle are parallel to each other again. And so convective acceleration occurs when flow is non-uniform. We could say that convective acceleration causes non-uniform flow, or you can expect to see convective acceleration when non-uniform flow is occurring, in the same way that unsteady flow, which means a change in velocity with respect to time, is caused by local acceleration. So here's that table that I said we'd gradually start filling up comparisons over the next several lectures. And in the previous lecture, we only had the first bullet point on each side. In comparing uniform and non-uniform, last time we already dealt with the fact that it's a change in velocity with respect to position. That's the key characteristic that distinguishes uniform flow from non-uniform flow. Whereas steady versus unsteady, it's not so much about position, but rather it's about time. Okay, so the next bullet point here is talking about the kind of acceleration that causes either non-uniform flow or unsteady flow. And it's convective acceleration, like the nozzle that we just looked at, that causes non-uniform flow. And if a fluid particle is experiencing unsteady flow, that's because of local acceleration. So we'll continue to compare and contrast and then identify how these series of differences kind of culminates in which equation we use to answer the question, what's the pressure at a certain location in the flow field? So here's an example that we'll take a look at. This is that same nozzle, This time, though, we have a little more specific information about what's going on inside the nozzle. This equation that's provided tells us the velocity as a function of position and also as a function of the initial inlet velocity. So U naught is the initial 10 meters per second. And so what this equation is saying is the nozzle has a certain length, L. And in the problem statement, it tells us that L is 0.5 meters long. And so if it's 0.5 meters, we're interested in, at the center of the nozzle, what is the convective acceleration. And so in order to find out the convective acceleration, we're going to have to, first of all, find the velocity at the center of that nozzle, because the definition for convective acceleration is it's the velocity at a certain point multiplied by du dx. So we have to evaluate the velocity and how it's changing as a function of position at a certain location, and then multiply it by the velocity at that location. And that'll give us the units we need for acceleration. And that's another thing I should mention, is whether you're talking about local acceleration or convective, the units are still meters per second squared. You still have the same units of acceleration that you've always come to expect. But it's a little bit unusual here, the convective acceleration. We're not as familiar with it. And so in this example, we're going to, first of all, with this equation, find du dx using the chain rule at the location of halfway, at x equals 0.25. And then when we find du dx, we'll also evaluate this function to find what is the velocity at the midpoint, and then multiply the two together. Multiply the velocity at a location by du dx at a certain spot. So any questions so far? This is one of the rare times I'm actually going to work the solution out on the board. As I do that, the solution will be on the recording, but I'm not going to show that to you all at once. I think it's better if we sort of step through it gradually. But if you do happen to come back over time and watch the recording again, it is there. This is one of the rare times that we actually use calculus in civil engineering. You know, the electrical engineers, those guys have it pretty bad because they're using calculus on a daily basis. But for us, it's maybe more of a rite of passage than a frequently used tool. Is there a question?
Yeah.
Uh-huh. Okay.
When we do this, I noticed that we relate it to position and time.
Mm-hmm.
What is this relation to area where the diameter of the pipe is?
Well, it's the decreasing cross-sectional area that's causing the increase in velocity. In Chapter 5, I'm going to emphasize this, what it's called the continuity equation, Q equals VA. And what that says is that the flow rate is the velocity times area. And so from that, we can find that the velocity is Q divided by A. And so in that nozzle, whatever goes in the nozzle has to also go out. So if you put in 1 liter in and 1 liter out, then 1 liter will have to come out. Like inside an enclosed space, there's no capacity for storage or accumulation. And so you're asking about, you know, the area and the diameter. It's the decreasing diameter that decreases the area, and then that in turn is what increases the velocity. I don't know. Why don't you, I'll show you this way of calculating it, and then if you can find an easier way, I'd be delighted to see it. All right, so what we have is, in the example we just looked at, we have that the total length of the nozzle is 0.5 meters. The initial velocity is 10 meters per second. And we're going to evaluate at the location of x is 0.25 meters. And then the equation that we have for velocity is that the velocity at a certain point in the flow field is the initial velocity and then 1 minus 0.5x divided by L. So we know that when the water comes out, it should be going 20 meters per second. Let's check this equation to make sure that we're going to get 20 at the exit. And so at the exit, then x will be equal to L. At the exit, that just means that the position within the nozzle, if we sketch that nozzle back on the screen again, L is the entire length, and then x is just some distance into the length of the nozzle. So when x equals L, that's like we're saying u naught divided by 1 divided by 1 minus 0.5. So it's u naught divided by 0.5. So it's going to be double the velocity. So it will, if it's 10 going in, it'll be 20 coming out. So far so good. That the equation at least makes sense with the two positions that we do know velocity. Okay, and then the other thing that we sort of are keeping in the back of our mind is the fact that convective acceleration is the velocity multiplied by du dx. And this is the rate of change with respect to position. All right, so to find du dx, we can use the chain rule, which says du dm multiplied by dm dx. So temporarily, we're going to be assigning the variable m for our equation of velocity we're going to let m equal 1 minus 0.5x divided by L. So this denominator is kind of complex. It's got x and L in it. And so we're just going to say, let's have that whole denominator equal this new variable m, just temporarily. And then we'll make the substitution again after we've taken the first stab at it. So what we end up then is u is going to be u naught minus divided by m, which is the same as u naught to the m to the minus 1 power. So we've just done this substitution. The whole denominator we're calling m, and since it's in the denominator, that's the same as m to the minus 1 power. Therefore, du dx is going to be d u naught to the m minus 1 power dm, and then d 1 minus 0.5 x divided by L dx. So here is the basis of the chain rule. Remember, m is just this expression here. And so dm here is the dm. Since that's already in terms of x, and this is dx in the denominator, then that's the way we want it expressed there. But then in the first one, we're still referring to it as m, rather than the thing that we assigned to m. Okay, so now we just have to do some changes here. Instead of it's m to the minus 1 power, then we move the exponent down in front, so it's minus 1 u naught m to the minus 2 power. And then this part of it, if we take the derivative with respect to x, then it's just negative 0.5 divided by L. Okay. So then we know that for m is equal to 1 minus 0.5 x divided by L, then du dx is negative 1 to the u naught multiplied by u naught, 1 minus 0.5 x divided by L squared times minus 0.5 divided by L. Okay, so those are the two pieces. Just making sure everything follows. Yeah, we're moving m back down to the denominator, so it's m squared, and we're substituting what m is equal to back in place of m. And then if we combine these two parts, it's 0.5 u naught L1 minus 0.5 x divided by L squared. We're getting closer. Now we have to evaluate it at a certain location. So it's at x is 0.25 meters and L is 0.50 meters. And so the acceleration that we're doing is going to be the velocity multiplied by du dx. So the velocity multiplied by du dx is going to be the equation for velocity that we were originally given. So that's still there. 0.5 u naught squared divided by 0.5 meters, 1 minus 0.5. All right. So we were multiplying in this step. We have du dx, and we multiply it by the equation for velocity. So we had u naught in both of them, both in u and in du dx. That's why it's u naught squared. And then we've substituted in the positions that we know. The x is 0.25, L is 0.5. And so that reduces down to u naught squared, 1 meter times 0.75 cubed. Okay, so that is 2.370 u naught squared. And now we have a value for u naught. We know that u naught is 10 meters per second. So then that is 2.370 times 100, because it's 10 meters per second squared. So it's 237 meters per second squared is the convective acceleration at the location that we're interested in. It's not always as complicated as that, because sometimes du dx is given directly at a location of interest. Oftentimes in problems, the velocity gradient, as it's called, du dx is called the velocity gradient. Sometimes the velocity gradient is just specified at a certain location, and then what you'd need to do to find the convective acceleration would be just to multiply the velocity gradient by the velocity at a certain spot. But in this case, we kind of had to go to a little bit more length to find the velocity gradient. So that's convective acceleration. Now let's just remind ourselves of a few definitions. First of all, steady flow is when velocity is constant with respect to time. Uniform is when it's constant with respect to position. And so the local acceleration is the change in velocity with respect to time. Convective is with respect to position. And then steady versus unsteady, uniform versus non-uniform. What we're going to be headed towards at today's lecture and tomorrow is Eulers Equation. And Eulers Equation will allow us to know when the fluid is accelerating sideways or up and down, how the pressure is changing. And also Eulers Equation can be used to tell you what the water surface is doing in response to an acceleration, because it's not just the pressure that changes, but if you think about a tank of water, for example, and if it's motionless, then the water surface is even with the ground level. But if you begin to accelerate it in a certain direction, for example, if you accelerate it to the right, then that water surface is going to slosh to the left. So there would be a new water surface because of the acceleration. And so Eulers equation, which we'll get into a lot of detail in the next lecture, just sort of an early taste today, it tells you what the slope of that water surface is going to be. Or you can use it to find out what's the pressure distribution across the bottom of a tank. Later on, after we finish with Eulers equation, then we'll do Bernoulli's equation. And many of you may already be acquainted with Bernoulli's equation, like at science museums, they often talk about it. They'll have like the little ball that's levitating with a jet of air, or sometimes people hear about Bernoulli's equation when they're talking about airfoils and the lift that's generated from wings. And so it's a little bit maybe better understood by people who are already coming in. Eulers equation sometimes is a little more challenging though. So here is a graph that represents that you can have both steady and uniform flow at the same time. That would be this first condition here, steady, uniform flow. And so that means that the velocity is constant both with respect to position and time. And remember that it is the parallel walls of a pipe that would give you uniform flow. And it is the changing cross-sectional area of a pipe that would cause a change in position with a change in velocity with respect to position. And so that's why here for the non-uniform flow row, these two cells, that's why we have the diameters decreasing. But you can have unsteady, non-uniform flow. And that's pretty complicated because when you have unsteady, non-uniform flow, what that means is that the velocity is changing both with respect to position but also over time. So imagine this valve here. It's a nozzle that maybe would be at the end of a fire hose so that the spray can get up into a building that's on fire. So when a firefighter starts opening up the valve and water is gradually increasing in velocity, then you will see at this location in the center where the fluid is being accelerated, you'd have both unsteady and non-uniform flow, which means there's both a local and a convective acceleration at the same time. So Eulers equation is what we can use to find out the response of fluids to local acceleration. Now, the hydrostatic equation is what we've used before to find out what's happening with pressure. But it can only be used when fluid is static, meaning when it's not moving. Here's a tank of water, and we'd simply say that the pressure at a certain location would be the unit weight of the fluid multiplied by delta H, where of course the unit weight is the density of the fluid multiplied by G. So actually there already is an acceleration built into the hydrostatic equation. It's just that the acceleration that we're talking about in the hydrostatic equation is the acceleration of Earth's gravity. But when a fluid is actually moving independent of that, then there may be accelerations other than gravitational. And so take, for instance, what if the tank that's pictured here was accelerating upward at 9.81 meters per second squared. So delta H is 1 meter, and it's not just motionless, it's accelerating up. I'd like you to take a stab at guessing what is going to be the pressure at that depth of 1 meter because of the fact that it's accelerating upward. So do that calculation. See if you can calculate it. Okay, if you're still struggling conceptually on how to calculate this one, let me remind you of the hydrostatic equation. So delta P is delta H times gamma. We already know that. And gamma, of course, is density times G. So if we have not just gravity, what we could do is we could substitute, we could sort of transform the hydrostatic equation into something that says, let's keep track of all of the vertical accelerations, not just G, but G will still have an effect on this tank, but then there's another acceleration as well. So just as like an experiment, a mental experiment, think about an astronaut who's accelerating into space. And the pressure on the back, as they're laying down in the chair, before they blast off, there's some pressure on their back, but as the rocket accelerates upward, then they call them the G forces, but really it's just acceleration, is pushing so that there's even a greater pressure between the back and the chair. And so here, there's a pressure just due to the static conditions, and that's really because of Earth's gravity. But then when you're accelerating up at 9.81 meters per second squared, then really what it's saying is that it's going to have double the effect as you move downward 1 meter through the fluid. Then the pressure increase is twice of what it would have been if it was stationary. So the sum of the acceleration in z, there's g plus this additional 9.81 meters per second squared. So what we should get from that is 19,620 newtons per meter squared. Because the density of the fluid is 1,000 kilograms per cubic meter. The delta H is 1 meter, and then like the sum of the accelerations is going to be g plus the additional 9.81 meters per second of its accelerating upward.
So is this experiencing 1 G of force or 2 Gs of force?
I guess you could say 2 Gs, because 1 G is what we experience when we're just standing here, right? But then if we're accelerating upwards at an additional 9.81 meters per second squared, then I guess that would be an extra G, so 2 Gs. Mm-hmm. No. Yeah, you know, like those, the Vomit Comet, that plane where they go and then they sort of go through like a downward acceleration so that astronauts can practice weightlessness. That's a 0G environment. And the interesting thing is that in an environment like that, then there's no pressure change as you go downward through the fluid. So if this tank was going down at 9.81 meters per second squared, then the pressure would be the same everywhere in the tank.
So if you're accelerating downwards in the same direction as the same acceleration as gravity, that's not
Mm-hmm. Yep.
That makes sense.
Now, I got to emphasize this warning. This conception of the hydrostatic equation where there's an additional vertical force component, only use that in a situation where the only acceleration is vertical. Most of the problems you're going to have in the homework and so on will include accelerations that are side to side. You do have one homework problem, we'll talk about the key ideas here in just a minute, where it's only a vertical acceleration, and you can use this, or you could use the full Eulers equation. Just to be clear, this is not Eulers equation, not yet. Eulers equation is a lot more rugged and like it can handle more situations. It's not constrained only to vertical acceleration. But this is a useful way of thinking about why the pressure is increasing in the first place. Now, next time in class, when we start getting into the full-blown Eulers equation, what we're going to do is think about an element of fluid that exists in 3 dimensions. And so at the start, let's look at these axes descriptions here. We've got the x direction, the y direction, and the z direction. It's x, y, z. And this cylinder, like a fluid element, is oriented in some L axis. So L is just a direction that's other than along x, y, and z. It has some component of all 3. So what you can see is that there's a cylinder of water, and on one side it's got the pressure on one side of it is P plus delta P. On the other side of it is P. And so there's going to be a change in pressure that Eulers equation is going to try to explain. And the reason for that change in pressure is going to be because of acceleration in the L direction. So we'll account for, in Eulers equation, we are going to account for the weight of a fluid element, and we won't neglect gravity. It's just that Eulers equation will enable us to find out the incremental change in pressure due to acceleration in any direction. And this is just picking the L direction as an illustration that it could be really any orientation that the acceleration occurs. So when we go through Euler's equation, we'll look at questions like, what's the mass of the fluid element? Because it'll have a certain volume, and we're interested in the direction of the weight. We'll look at the difference in the forces acting over a cross-sectional area. And remember that force, F equals ma. And so if we have a certain mass of a fluid element and we have a cross-sectional area that it's acting over, then we can find the forces that are applied to cause an acceleration. And then the directionality in the change of pressure is important, because when we're doing Euler's equation problems, we have to be really careful about convention when it comes to motion to the right would be considered, for example, if we're talking about the x-axis, motion to the right is considered a positive acceleration, motion to the left is a negative acceleration, and then likewise, vertically speaking, up is considered positive, down is considered negative, and we'll have to be very, very particular about keeping track of directions and applying that to accelerations when we start applying the Euler's equation so that the pressures we calculate are correct. All right, this is one of the homework problems that you have due on Tuesday of next week. I'll mention to you that at least in the copy of the book that I have, the figure is wrong. So don't be thrown off by the difference in the problem statement and the little sketch that they've provided. In the problem statement, it says that there's 10 feet of water, but I think in the drawing that it shows in the book, it lists it as 3. But it's 10. Use the written description in the problem statement. So it's like a cylinder of water that has a piston at the bottom. And the piston is accelerating upward at some acceleration. We don't know how quickly it's going up. But because it's accelerating upward, what it's doing is it's pressurizing that liquid in a way that's different from how it would normally be pressurized if it wasn't accelerating. If it wasn't accelerating, then we could just use the hydrostatic equation, and that would be easy. But here, what we know is it's 10 feet depth, and at the bottom of the piston, it's 8 psi-g. First of all, what does psi stand for? Pounds per square inch, and so it's lb per in. All right. Now, our distance of 10 feet suggests that we should think about pressure not in terms of inches, but in terms of feet. So how do you convert pounds per square inch into pounds per square foot? 12 inches per foot, right. So if you have, there's 12 inches in a foot, and it's a square foot, that means that 1 pound in a square inch is the same as 144 pounds in the square foot. So keep that in mind, that 1 psi equals 144 psf, pounds per square foot. Because you'll be working this problem with distance of 10 feet, and so you'll need to convert the pressure into pounds per square feet. The G, what do you suppose the G means? Gauge, right. What's the significance of that? What's that? Okay, so we're ignoring atmospheric pressure. And here's the little clue that this is open to the atmosphere, those ripples at the top. So that tells us that we're going to assume that at the top, pressure is 0, and at the bottom, the pressure is 8. Okay, so we have a delta P now. The water depth is 10 feet. The pressure at the bottom is 8 psi-g, which we can convert to PSF easily enough. And what the question is asking is, what's the acceleration that causes this situation? For a certain depth and a certain pressure that they've measured, from that we should be able to back calculate the acceleration that's causing the pressurization at the bottom of the cylinder. We don't work in the traditional units very often, but just as a reminder, G, 32.2 feet per second squared, and then the density of water, 1.94 slugs per cubic foot. That's something that we did see earlier in the semester. Not sure where the per cubic foot went, but there it is now. Any questions so far?
I have one.
Sure.
In the syllabus it says 38, so you want us to do problem 39 instead?
Does it say 38?
Unless I'm reading that wrong.
Yeah, do 39. Thanks for pointing that out. Let's see what I have here. I'm glad that you noticed that. Yeah, do problem 39, not problem 38. So as it says on the slide there. So are the rest of them okay? 6, 7, 14, 27, and 39. Yeah. Okay. Great question. Any others? Okay, now here is the sort of the yes, go ahead.
Or like, I know the exam 2 is pretty far away, but do we need to know the traditional and SI units for like density and gravity? Not that hard.
No. If I gave you a traditional problem, I'd tell you the density of the fluid. I don't think you've used that 1.94 slugs per cubic foot enough that it would be reasonable to have you know it. I provide that. All right. So this is what we've sort of adapted our hydrostatic equation to so far. What's the limitation of this expression? Only when the acceleration is vertical, and it is here. This cylinder is confining the movement of the liquid to up and down because of the cylinder walls. And so there's no side-to-side acceleration. The full-blown Eulers equation, which we'll get to next Tuesday, takes us way beyond, but you can solve it this way. And so there's going to really be two different accelerations here in this problem, because there's G, which is causing some of the pressure change, and then there's the movement of the liquid, which is causing the other part of the pressure change. So here where I say the sum of the accelerations in Z, part of the pressure change is explainable just by G, but then this is saying find the acceleration that's causing this pressure. That means the acceleration of the cylinder itself. How much is the piston accelerating the liquid upward? Other questions about this one? Okay, that's it for today. Just remember that the assignment includes 39, not 38. I'm glad you caught that. And I'll collect that from you on Tuesday. Have a good one.